Sangam Prabha. Digital India. Educated India.
So we are talking about graph algorithm. We have, in the last class, we have discussed the graph. We introduced the graph, just the basic introduction to graph. So graph theory has another area where you can study later stage if you have opportunity to study the graph theory. It is a very fantastic area. There are lots of applications there in using graphs. And this will, we are talking about one particular graph problem, which is called minimum spanning tree problem. So what is that? That problem is we have given a graph, which is usually a unordered graph. There is no direction. We can handle with direction also, but in this Prim's algorithm, we have no direction is given. So this unordered graph is given, and on each of the edges, we have a weight. So we have a weight function which can take, which is a weight on each of the edges, and then you have to find the minimum spanning tree. So you have to find the spanning tree. Spanning tree means which is, it's a subgraph, acyclic subgraph. It has no cycle. Acyclic subgraph which is covering all the vertices. That's why it is called spanning. And what is the weight of that tree? Weight of the tree is the sum of the weight of all the edges in that particular tree. So if we take the sum and we want to minimize, we have to choose the tree. There could be many trees covering all the vertices. So we want to choose we want to get the minimum one. We want to choose the minimum sum tree, and we want to choose the minimum sum, like minimum spanning tree. So that is the idea, and we have taken some example in the last class, but we want to move to a proper algorithm to find that. So that algorithm we will discuss today is called Prim's algorithm, and this is greedy approach, greedy algorithm. So for greedy, we need a hallmark there. We need an indication that okay, we should go for greedy. That hallmark is a locally optimal choice is globally optimal. So this is the hallmark for greedy technique. So any greedy algorithm should have this type of indication, this type of hallmark. If our problem has this type of hallmark, then we can think for applying the greedy approach. So here in this context, how this will be, how we can establish this locally optimal is globally optimal. How we can prove this? To prove this, this meaning of this is, suppose we have a graph. We have a graph G, which is consist of set of vertices, set of edges, and then edge are weighted by some weight function W, and we take some A set from this set of vertices. So A is a subset of, we take some A set of vertices. A is a subset of V. V is the set of all possible vertices. And there is a complement. A complement is basically V minus A, set of all other vertices which are not in A. Now, this theorem is telling, if we consider all the vertices, all the edges which is having one part in A and another part in A complement, these are called bridge edge. If we consider all such edges, okay, if there are, so if there are some edges which are connecting, U is here, U is here, UV is an edge, and V will be here. So consider all such edges, and this theorem is telling that among these edges, all the edges has some weight. Among these edges, the edge which is having the minimum weight, that will be in the minimum spanning tree. That has to be in the MST. So that is the theorem, and that is the greedy choice. So that is the locally greedy. If we have to choose an edge in order to cover a vertex, we start. The idea is the Prim's correctness of Prim's algorithm is on this theorem. This theorem is the correctness of Prim's algorithm. So idea is we start with a vertex, then we consider all the other all the vertices which are directly connected with this vertex. Then we take the minimum edge of that degree of that vertex. So that minimum edge we capture. We capture this U in that A, and slowly we grow the tree. So that is the idea. Now we have to prove this. So this is the greedy choice. This is the locally So because if we have to choose a edge and we are looking for the minimum spanning tree, so obviously we should choose the minimum one. So that is the greedy choice, and that is the locally optimal, because we are looking for the minimum one, minimum spanning tree. So that we have to prove. So among these edges, suppose UV is an edge, which is a bridge edge, was one component, one node is here and another node is here. So if this is the least weight edge among the all such edges which are connecting from A to direct connection edge, A to A complement. So among these, whichever is the minimum, so that is our that has to be in the minimum spanning tree T. So that is a theorem. So let us prove that theorem. Then we will see how we can. So this is basically the idea behind the Prim's algorithm, and this is a greedy approach, because we are greedy, we are locally greedy. So how to prove this? We can just prove this by drawing this figure. So suppose we have a graph like this. Okay, even we can prove using we can just justify if we just yeah. So if this was our MST, if you recall from the last class, this was our MST we have constructed. Now, if you take any A, if you take some A, suppose A consists of say these three vertex. Suppose this is our A. And then what is the A complement? A complement will be this one. Now, the theorem is telling the bridge edge. Who are the bridge edge? This is one bridge edge, this is another bridge edge, this is another bridge edge. So there are three bridge edges. Among these, who is the minimum? 5 is the minimum. So a theorem is telling 5 should be in the MST. Yes, 5 is in the MST. You can check with any other A. If we choose this to be your A, just another example, but we can prove it. If we choose this to be our A, only one vertex, and remaining are in A complement. So what are the bridges? It is all our bridges. This 7, 15, this. So among this 7 has to be there in the minimum spanning tree. Like this, we can take another A, like if we take, for example, these two vertex as our A. And the remaining all our vertices are in A complement. Now, who are the bridges? Bridges means one part will be in A, another part will be in A complement. So this 14 is in bridge edge, then this 8 is on bridge edge, then this 10 is on bridge edge, like this. So among this, who is the minimum? 8 is the minimum. So yes, 8 is the minimum. You can just easily verify this. Anyway, we can prove it. Let me go back to that slide. Yeah, we can prove it just by drawing this picture. So suppose this is a minimum spanning tree, and we just consider some vertices as A. A is this green vertex. So these are A vertices, and this orange, yes. So these are our A complement. I mean, which are not in A. Now we take a vertex which is the among these bridge edge. This is the least weight edge. Suppose we consider the bridge edge. So there are bridges like this bridge edge. This is one bridge edge. These are all bridge edge. This is one bridge edge. This is one bridge edge, like this. So among these bridge edge, we take the least one. Least one is UV. So suppose it is again the same technique we have used for the last class to show the optimal substructure. So suppose this is not there in the minimum spanning tree. Suppose this edge is not there in the minimum spanning tree. So we can just remove this edge. We can just remove this edge, and to remove this edge, we have to cover this. Otherwise, this will be disconnected. So for that, what we need to do, we need to take a path from U to V, because V this is a connected graph. I mean, tree is a connected acyclic graph. We should not have disconnected component. That is called forest. So tree is a connected acyclic graph. So we can choose. We have to connect V with our this tree. We have to choose a path from U to V like this. Suppose this is the path, and in this path, this is one of the bridges. Okay. So then we instead of this, we take this path. But in that path, we have one bridge edge. So and also we have considered some of the other edges. So that will cost us more, because this was the minimum. If we take the direct this one, then that is minimum instead of taking another bridge edge, which is not least one, because least one is this one. So that is the contradiction. That is usually called cut and paste technique. We just use the another path to cover this, and that is the higher weight of the spanning tree instead of this one. Okay, so this is the rough idea of the proof of this. You can do it by induction also, this proof. Okay, now come to the, so this is the idea behind the Prim's algorithm, this theorem. This theorem will give us the correctness of this Prim's algorithm. So basically the idea is we have to maintain a maintain a priority queue for V minus A complement. We start with a vertex, we put it in A, that is the starting vertex. That is, say, any arbitrary vertex we can start with, because there is no restriction on the starting vertex. So we can start with any arbitrary vertex, and then we put it that in A basically first. So basically maintain. So initially all the other vertices, initially every vertex is in A complement. So we need to maintain a priority queue. This could be simple array also. Okay, and what we key? We key each of these vertices with the weight of the least weight edge connecting with it vertex in A. So the idea is, so we this is our A, which is starting with a vertex S, and all the remaining vertices are in A complement. This we can simply consider as an array. This priority queue we can just simply consider an array. If we have n vertices, we have an array of size n, v1, v2, vn. Okay. Now what we need to in the priority queue, how to maintain this queue? What value we'll put it here? The key value is the value is the least weight edge connecting it to this V. So we take a vertex V over here in this. So this V could be connected with many vertices within A. Sorry, this V, only V. So V could be yeah. So V could be connected with more than one vertices in A. Okay. So among these, whichever is the minimum, we'll take that as a value over here. That is our key value of that corresponding node, key value of the corresponding vertex. So that is the way we key each of the vertices which are in this priority queue. Initially, everybody is in the priority queue. We key each of these vertices by just putting the least weight edge, which is connecting with V and E. Sorry, this is a complement. V minus A with the A. So initially everybody we have to put in this thing. Initially everybody is in queue in the array. This queue could be heap also. We'll see that. So let us consider. Yes. Any question? Okay. Let us put every vertices in queue. So that could, just for the timing you can think that's as it. So we take an array. Now we haven't started yet, so we have no idea what about this key value. We have no idea about this minimum age, everything. So we initialize this by infinity. The key value of this, all these are infinity. So we initialize. So this is V. V is over here. So we initialize each of these values as infinity because we haven't started yet. Except one vertex which we want to start with. Say that vertex is S vertex. So that vertex key value we put is 0. So that when you extract the minimum, that will come, because we want to start with a starting vertex. That is nothing but a starting vertex. So that is the initialization step. We just put every vertex key value to be infinity because we haven't started yet. This is the initialization. And except one vertex, which is the starting vertex to start with. That is our starting vertex. We want to start with that vertex and slowly we grow the tree. Now, if we extract, now while Q is not empty, because Q is we are putting everything in the Q. So obviously in the first sort Q won't be empty. So what we do, we extract the minimum. So when we extract the minimum in the first sort, the S will be extracted. And extract means we delete we delete from this set Q, and then we put it in, A. So A is a set for which we cover the vertex basically. So here is a set, and here is a Q set. Initially everything is in Q. Q is basically a complement. So we just, in the first step, this step, when we extract the mean means we take the minimum one is S basically in the initial stage. So S will be extracted from this Q and S will be added. So extract mean means we delete from Q and we are adding in this set A. If you want, you can write another line that A is initialized by empty, and then A is added with this U. First U is our S. But after some time it will be a new U. But anyway, this is our U. This is our U, which is extracted, which is extracted from Q. Okay. Now U has some adjacency vertex. That is come from adjacency list. Okay. U has some adjacency vertex. So this is what is called decrease key step. So we go to each of the adjacency vertex of U. So it was having some degree, because it was having some bridge edge with A, which was minimum and initialized by infinity because nothing was. Now we have a new bridge edge. We have a new bridge edge because U is just got inserted into A. So this is a edge which we should consider. Now if the weight of this edge is WUV, right? WUV. If the weight of this edge is less than what it was having earlier, I mean initialized by infinity, but slowly it is getting updated now. So if weight of this edge is less than the key value it is having, then we change that. Then we replace the key value by this weight, because then this is a better bridge edge like that. So we replace this key value by this, and this is the decrease key, and we put a pointer that who is responsible for this change. We change the key value of this by this new weight of this connection. Now who is responsible? This U is responsible. So we put a arrow over here to indicate the responsibility vector, because that eventually will give us the shortest path. That eventually will give us the shortest path with the connection, with the responsibility vector. So this is required because earlier this degree of U may be by changed by some other vertex. Now we have a better one. So this should be added in the H, MST with a hope, if not change again in future. So that's why we need to get this H, we need to take this vertex. For U vertex also we need. Otherwise we cannot report that H. How to get the H? H means two vertex. So we have to get two vertex. So for that we need to take this help of this responsibility vector. So this got changed, this degree of this or key value of this got changed, and who is the responsible for this change? This U, so that we can get this H. If it is ultimately, if it is the H has to be in the minimum spanning tree. That's it. So this is the this step is called decrease key step, and then finally when the key will be, when everybody will be included in A, that means we are done. Then the this queue will be empty. There is nobody in the priority queue. Then we stop. So this loop will stop at when there is no one to capture. So the idea is we start with the vertex, and we consider all the adjacency vertex of this. Then we take the minimum one, the bridge edge. So we capture that vertex in. If this is the minimum one, we capture this is in U, this is in A, this U. Then we consider, once this is included here, this is a new member in this A, then we have to take all the bridge edge, all the edges, a degree of this, which are not in, which are adjacency vertex of U, which is the new member, And maybe you can check, add another condition that which is not in A, because for A we are done. But anyway, you can have a double check over here. So finally, capturing all the vertices, we can report the MST, which is coming from that pointer. We can just take this because we have to cover all the vertices. So all the vertices as this, we have assigned this a pointer in order to get that particular edge, which is the response, which will be in the MST. So this is the greedy choice. So this is the locally optimal, because and this is the correctness also by that theorem, because that theorem is telling if you choose this edge to be the in the MST, that will be in the this locally optimal will be the globally optimal. Okay, so this is the pseudocode for Prim's algorithm. We'll take a quick example, then we'll go for the time complexity. So let us take a quick example, then it will be more clear, this Prim's algorithm. So this is our graph we have considered from the last class. So this is our graph we have to, and these are the weight on the graph, and we want to apply the Prim's algorithm on this graph. So we have to start with some starting vertex S, small s. So this is our small s. We start with a vertex. You can choose any other vertex as a smallest. So in this example, we are choosing this vertex as our smallest. So, and the key value of all the vertices we keep to be infinity. That is the key initialization step, and that is the and then I accept one vertex which we want to start, the starting vertex, that is the 0. Now everything is in Q now, because Q is V basically. Now we want to extract a vertex, and we want to extract a vertex which is minimum among this key value and put it in A, capital A. So initially everybody in Q. So and then who will be extracted? Everything is infinity except this 0. So 0 is the minimum. So 0 will be extracted. So this vertex will be first captured. So this vertex will be put in A. Now once a vertex is put in A, so what we do? The idea is this just come. Idea is we just consider all the vertices which are connected with this new vertex. I mean this newly insert vertex. So among this, suppose this is V. So we consider all the vertices which are adjacency in the adjacency list of this vertex. So this one, this one, this one. These 3 vertices are basically in the adjacency list of this. Now we check their degree. Their degree was infinity. Now we have a bridge edge, which is connecting with A and A complement. So that bridge edge is this. Let us consider this vertex. Let us consider this is our V. So for this V, we have only one bridge edge. So this is 7. It was having infinity. So we just change the degree of this to be 7, because 7 is better than infinity. So that way we do, and we put a responsibility vector. Who is responsible for this change? This vertex is responsible for this change, because ultimately we need to get the edge to report the MST. So this is the responsible. So we have a change in the key value of this vertex. We have a change in the key value of this vertex. But who is the responsible for this change? This is our U. Because let us say somebody else can have better weight. We'll see that. So in that case, the edge will change. So that will be getting from this responsibility pointer, this vertex. Who is the responsible? So this U got changed, degree of U got changed, and who made this change? This vertex. This is degree of V is changed. So who made this change? This U. So we put a pointer over here to indicate the responsibility. So similarly, this vertex, done. So now we have to again extract the to get the next vertex. We grow the tree. We start with the vertex S and slowly we grow the tree. So among these, who is the so everybody is in Q, A complement except this vertex. So if we extract, then the minimum is 7. So 7 is our new U. So 7 is our U now. And then we consider all the vertices which are connecting to this U. So 7 is now capturing U. Now we consider all the vertices which is connecting with U. So these are the adjacency list of U. So among these, who are the vertices there? So this vertex, this vertex, this vertex, even this vertex, but you can ignore that, but it is already in A, but you can just check that also to cross verify. Okay, so this was having a this u was v was having a weight this key value infinity. Now we have a better one, so we replace this by 9. So let me just capture 7, and then we replace this by 9, and this was infinity. Now we have a better one, replace this by 12, and this is the responsibility for this. If this is the u, sorry, if this is the v, and this is our u, now we just change the key value of this v, and who made this change? This u. So we have a this responsibility vector in order to get the MST finally. Anyway, so let us just move forward. So this will change this vertices degree of key value of these vertices like this. So next we'll again extract. We'll check whether Q is empty or not. Q is not empty. There are all the 6 other vertices are in Q still. So we extract the minimum. So minimum is again who is the minimum now? Minimum is 5. So this is our new U. So minimum is 5. So we capture this vertex as in A. So extract in from Q means we are adding in A. We are unioning in A. So that is the thing. Now this is our new U. Now we consider all the vertices which is in the adjacency list of this. So suppose this vertex. So yeah, so this vertex. So now you see here this vertex. Who are the adjacency list of this? So slowly we can just, yeah. So let us consider this. So this vertex, I just take this vertex first. Okay, suppose this is our U. Yeah, this is our U, and now suppose we take all the adjacency vertex of this. So this is our V. Now it was having a key value 12. That means there was a bridge edge from A to with this vertex which was minimum 12. Now we got another bridge edge because this just now this guy is included in A. So we have another bridge edge whose weight is 6, which is better than 12. So we must change that. We must decrease that. So we must change this value to this key value to 6, and we must put a, because it was having another vertex was responsible for this 12. Now this vertex is responsible for this 6, but this is a new edge. So if it has to be in MST, this should go instead of this. So this is a new edge. So we must delete this pointer. So we can have another pointer over there to indicate the number, just vertex number. So we must delete this pointer. So now we must put this vertex, this whatever number was in the responsibility vector of changing this vertex. So that is the idea. So this got 6. Similarly, this got 8. This got 14, like this. So we continue like this. We take the next one. Next one is 6. And we check, but for 6 every adjacency vertex are already in A, so it should not bother about that. And then this is next minimum is 8, and then we check all the adjacency vertex. We change this one. This was responsible by this vertex 14, but we have a better bridge edge 3, so this should change, this key value should change to 14 through 3, and this is the responsible for this. In order to get the, we need to store it, otherwise we will not get the H. To get the H, we need to have both U and V. Yeah, so that's all. So next this will be the minimum 3, but for 3 all the vertices which are adjacency of 3 is already covered in A. So next one is 9. So same 15. Fantastic. So we got the path. So finally this responsible vector that H UV will give us this minimum spanning tree. So this is the Prim's algorithm. Any question before we go to the time complexity? This is the greedy. I mean, we apply the and correctness of this is that theorem that if we choose a that minimum edge has to be in the minimum spanning tree among the bridge. Any question before we move to the time complexity? Yeah, you can. My suggestion is you can start with any other vertex instead of this vertex we have started. You can start with any other vertex. Say you can start with 3. Then you can capture this smallest edge immediately. Anyway, so you start with other vertex and then you slowly grow the tree. So that is the idea of Prim cell. Okay, if there is no question, we can go for the time complexity of this code. So how much time it is spending. So this is the piece of code. We want to get the time complexity of this. So, so this is the initialization step. So how much time we are spending in the initialization step? We are just order of v times, and the remaining that putting some value over there. So it depends on the way we are implementing. Like this is the, if we put it into the array. So let us, for simplicity, let us consider a array for the time being. So our Q is an array, or we put every vertices in an array. This is our priority queue. Our Q is in simple array. Then we'll first check what is the time complexity. Okay. So now what we are doing, we are going to, so this is V1, V2 like this. So we are, some vertex is our S. So we are just going to each, sorry, infinity, putting infinity over here, every vertices, except one vertex, which is, we are having the starting vertex like this. So this will cost us order of v times the number of vertices. If number of vertices is n, order of n times. Okay. Now here there is a loop over here. So this loop is how many times? This loop is v times, because every time we are extracting one vertex and we are capturing in A, and this will continue until the Q will be empty, and Q is initialized by the all the vertices. So this will be obviously order of v times, this while loop. Okay. Now we are doing some extract mean over here. Any idea how much time it will take to extract mean? Anyone? How to extract mean? How much time we'll spend here in this? Sorry, here.
Sir, for a min heap, it will take constant time.
No, just, yeah, just for the timing we have array. For array, how much time it will take?
For unsorted array, it will take n. I mean v.
Yeah, it is unsorted, because we don't know, if we cannot afford the sorting, because in that case it will be again, because this is keep on changing, na? Because every time it is sorting is not a very lucrative idea over here. Every time you have to sort it after updating that decrease key operation. Yeah, so it is it is just an unordered array, so it will take order of n, order of v basically. Sorry, but again, as you said, we can do it something better called, if our data structure is a heap data structure, mean heap. If we store our queue as a mean heap, priority queue is mean heap, then we can extract by height of this tree, because the minimum will be there in the root. So if you get it by extracting, again we have to replace. So that will come. So depending on the data structure, this extract mean will take some time. So if it is array, just a linear time. But if it is heap data structure, especially mean heap, then anyway we'll come to that. Okay, now what about this loop? This yeah. So what about this loop for each of the? So if you take a vertex v, what we are doing over here? If you take a vertex v, sorry u, which is just now extracted, now we have to consider all the vertices which are in the adjacency list of u. We are doing this decrease key for that. This operation is decrease key. This operation. We are going to that particular v. We are going to that particular v, and whatever value over here, we are changing. So if it is array, then it is constant time. But if it is heap, then changing means we have to do the again the mean heapify property. It will take log n. So anyway, that will depend on the data structure which we are using. So this decrease key. But how many times we are doing this decrease key? Any idea? This operation is decrease key. How many times we are doing?
E.
Yeah, why E? Order of E basically, because this is how many times?
All the edges we are going once, so E.
but not that way. We are going once means maybe twice also, because we are basically, this size of this loop is nothing but summation of degree of u. This many times we are doing the decrease key, and u is for all u. This is the number of times we are doing this operation, decrease key operation. This we know, this is basically handshaking lemma. This is order of u. If it is a directed graph, it is 2u. Sorry, this is order of e, the number of edges, order of e. But if it is, yeah, so that is basically the size of this inner loop under this while, size of this inner loop. Okay, so this will just let me erase this. Yeah, so this is the size of this inner loop. So we need to do this by a degree of u, and this is for all u from because every time we are one by one capturing u. So this is basically the times we are doing this operation decrease q. So that will give us yeah. So this is the handshaking lemma. This is order of e. So this is order of e times we are doing this degree of size of e. So this is the handshaking lemma, we know. Yeah, so now what is the total time? Time is, so this is order of u, v times size of v, sorry. This is how many time we are decreasing? We are decreasing v times. So size of order of v into time required for, sorry, extract mean. So how many time we are extracting means? V times. So v into time required to extract means. Depending on the data structure we'll be using, that will take this time. Plus, because this loop we are taking this decrease key operation, this operation is decrease key operation we are doing how many times? The summation of this many times. This is order of e. So order of e into time required for decrease key. Now depending on these two time will be depend on the data structure we'll be using. So this is the total time complexity for Prim's algorithm. Order of v into time required for extract mean plus order of v into time required for decrease key. Now tell me, if it is array, what is this time? Extract mean. We know only two data structure, array and heap. Yeah, please, if it is array, how much time?
Order of v.
Yeah, order of v. So if it is array, it is order of v, and the decrease key is just order of 1, because we know the position, we know v. This is number by 1 to n. If v is n, order of v is n, then this is order of 1. Then this will be v square, and this will be how much? This will be order of e. So this time will be for array. This time will be this is v square, order of v square, because this is order of v, and this is order of 1, and this is order of e, and order of e is bounded by v square. If it is complete graph, then we have v square. Otherwise, it is connected. So our lower bound big O is v square, but big omega is v. So this is dominating. So this is order of v square. So this is the time complexity for Prim's algorithm. If we use the data structure to be, if we use our priority queue, that queue data structure to be a simple array, unordered array. So that is order of. But if we use the mean heap, we know binary heap, that mean heap, we have studied max heap in our course, but similarly we can talk about mean heap, where minimum instead of maximum, we consider the minimum among the child. So anyway, so for that, this time, if we have a mean heap data structure, then this time the extract mean will take, because mean is the in the root. So if we extract it, then again we have to apply the mean heapify. So for that, order of v, and again to decrease key, if we just decrease a node, if we just decrease the value of that node, then maybe we have to apply the mean heapify there in order to bring the mean heap data structure. So that will cost us order of log v. So then the total cost is order of V log V, and then the order of E. This is the dominating because E is lower bound of E is order of V. So this is the cost, order of E log V. So this is the cost for the data structure we know. There are some other data structure and we can use the amortize analysis there. So that those things we haven't covered in this course. But the data structure we know so far is this is the best one. But if we use those amortized analysis of certain data structure, that will be E plus log V, which is very much faster. Okay, so this is the all about the Prim's algorithm, which is our greedy approach. So now, if you have any question, you can ask before we stop. Any question?
Sir, regarding tomorrow's lab.
Okay, so let me stop the recording first. If you have any question related to this lecture today, you can ask. Otherwise, let me stop the recording. Other concern. Okay, so in the next class, we'll discuss the shortest path problem. That is another graph problem. We'll see again the greedy approach for first two algorithms. Then we'll move to the dynamic programming technique for two more algorithms there. So we'll discuss that. Okay, so thank you very much. Let me stop the recording.